In this video, we're going to talk about the Cartesian equation of a plane, sometimes also called the scalar equation of a plane. The Cartesian or scalar equation of a plane in R3 is of the form ax plus by plus cz plus d equals 0, and the vector ABC is a normal vector, i.e. perpendicular to all the vectors in the plane. Imagine the blackboard in your classroom, if you will. If we drew any vector we wanted on that blackboard, and then imagined a vector sticking out perpendicularly from that blackboard, that vector sticking out perpendicularly would be normal to the plane. It would be perpendicular to any vector that you could draw. Okay? Well, let's show how they derive the Cartesian equation of a plane. We're going to let P naught, which is x naught, y naught, z naught, be a point on the plane whose coordinates are known. And we're going to let P, x, y, z be a general point on the plane that's different from P naught, which is x naught, y naught, z naught. Next, we're going to let n, which is ABC, be a normal vector to the plane, meaning that n is perpendicular to any vector on the plane. Now, since P and P naught are points on the plane, that means the vector from P naught to P is a vector on the plane. Since P and P naught are points on the plane, therefore P naught P is a vector on the plane, which means that n, which is perpendicular to any vector on the plane, dotted with P naught P should equal 0. Well, since P is x, y, z, and P naught is x naught, y naught, z naught, that means P naught P is x minus x naught, y minus y naught, z minus z naught. And since the normal vector is ABC, that means ABC dotted with x minus x naught, y minus y naught, z minus z naught will equal 0. Okay? Now, multiplying the x components, a times x minus x naught, plus b times y minus y naught, plus c times z minus z naught, we get the equation shown in the second line here. Ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. So that means we can say ax plus by plus cz plus negative ax naught minus by naught minus cz naught is equal to 0. And all of the quantities in this expression here are known. We don't know x, y, and z, but we know a, b, and c, and x naught, y naught, and z naught. So that means we can actually evaluate this bracketed quantity here, and we're going to call it d. And so that means we can state the equation of that plane as ax plus by plus cz plus d equals 0. So keeping that in mind, let's imagine we're given a plane in vector form as shown. Now, we want a vector perpendicular to both of the vectors that we know to be in the plane. So we want a vector perpendicular to both 3, negative 4, 6, and 1, 7, 4. Well, that's easy. That's exactly what the cross product is for. So we just determine the cross product of these two vectors, and using our cross product method that we learned in an earlier unit, we see that a normal vector to the plane could be expressed as negative 58, negative 6, 25. But we're not going to express it that way, because just like there's a convention to state direction vectors with the first non-zero component being positive, similarly there is such a thing with normal vectors as well. So although 3, negative 4, 6, 1, 7, 4, although 3, negative 4, 6 cross 1, 7, 4 is negative 58, negative 6, 25, to use the math convention, we'll say that our normal will be that vector times negative 1, and when we do that, that'll give us a non-negative our first non-zero term will be positive. Okay? So we're going to use it. So this is the explanation here, the same concept. We can use that as our normal vector, but it's a convention in math that we typically state normal vectors with the first non-zero component being positive. So we'll multiply it by -1, and instead we'll say that n is 58, 6, -25. So there's our normal vector. Well, what we were saying earlier on those blue sides is we can therefore say that 58x plus 6y minus 25z plus some unknown value of d will equal 0. To solve for d, all we have to do is plug in any point we know to be on the plane. Well, since -5, -1, 10 is a valid position vector, that means the point -5, -1, 10 is definitely a point on the plane. So plugging in this point to this equation is going to allow us to solve for d. And when we do that, we get d equals 546. And the Cartesian equation of the plane will therefore be 58x plus 6y minus 25z plus 546 equals 0. Every point on that plane, the x, y, and z, will meet that condition. So the Cartesian equation of a plane is usually written such that the first coefficient is positive, and it's usually reduced if possible. So for instance, had we had, instead of the equation as we've shown it, had we determined that the equation of the plane was 116x plus 12y minus 50z plus 1092 is equal to 0, then what we would have done is divided left and right side of that equation by 2, thereby reducing it the way you see there. So let's determine the Cartesian equation of a plane containing the points shown. Well, we want two non-zero, non-collinear vectors. So we can choose any two of the vectors AB, AC, BC, BA, CA, or CB, so long as the two vectors we choose are not collinear. So if we determine the vector between A and B, we see that it is -6, 1, -12. If we determine the vector between A and C, we see that it's 2, 6, -1. So to get a vector perpendicular to both of those, in other words, a normal vector for the plane, we will determine AB crossed with AC. And when we do that, we see that AB crossed with AC is 71, -30, -38. We have a non-zero first component, so we'll use that as our normal vector. Now, just as another little point here, let's just pretend that we had gotten AB crossed with AC equal to the vector 6, 2, 4. If that had happened, then we would probably say that n, we would just sort of make it a simpler collinear vector. We'd say 3, 1, 2. So sometimes something like that will happen, but this is not such a case. We can't really reduce 71, -30, -38 and still keep everything integers. So that will be what we call our normal vector. Okay, these numbers here, by the way, just to repeat, those were made up numbers that aren't relevant to the situation at hand. I was just trying to make a more general point. The situation at hand, this is our normal vector right there. No doubt about it. Okay, so now we know what our normal vector is, so that means we know that the equation of the plane will be 71x minus 30y minus 38z plus d equals 0. So we're just going to plug in any known point. Well, if you go back to the question, it told us that one of the known points is the point 523. So let's use it. We'll plug in 523. And when we do that, we'll solve for d, and we'll get that d ultimately equals -185. And that tells us that the Cartesian equation of the plane is 71x minus 30y minus 38z. That should be a z there. Minus 185 is equal to 0. Okay, now here's an interesting fact. The angle between two planes is equal to the angle between the normal vectors of those two planes. If I have plane 1, that creates normal 1. a vector perpendicular to plane 1. If I have plane 2, that creates normal 2, a vector perpendicular to plane 2. Well, the angle between the angle at the intersection of plane 1 and plane 2 will equal the angle at the intersection of normal 1 and normal 2. That is so convenient. So if we wanted to show that two planes were perpendicular, all we would have to do is determine the normal of the first plane, which is 2, 3, -4, and the normal of the second plane, which is 5, 2, 4. And we would just have to show that these two vectors are perpendicular to each other, which would then mean that the planes from which they came are perpendicular to each other. Very, very convenient thing in math. So, oh, and one other thing here, it's fair to note that pi is often used to represent a plane. You may have noticed by now when we talk about lines, we often identify them as L1 and L2 and then put them into their vector form. Well, when we talk about planes, we often talk about pi 1 and pi 2, and pi represents in this context plane. Okay? So, all we have to do now to show that these two planes are perpendicular is to show that the dot product of 2, 3, -4 with 5, 2, 4 is equal to 0. Okay? So, the dot product of those two vectors equals 0. So, since the dot product of the normal vectors is 0, therefore the normal vectors of plane 1 and plane 2 are perpendicular to each other, therefore the planes themselves are perpendicular to each other. Now we want to show here that the planes given are parallel but not coincident. So the first normal, the normal of the first plane, is 3, -9, 3. The normal of the second plane is 2, -6, 2. These two vectors are collinear, okay, because one is a scalar multiple of the other. So since they're scalar multiples, the planes are parallel. But this question is asking us, don't show that they're parallel, show that they're parallel and not coincident. So just like in grade 9, when you learned that two lines that are parallel but have a point not common to both, those lines are parallel and not coincident, i.e. parallel but not the same line. Same thing's true with planes. If you have two planes that you know to be parallel, but there's a point on one that's not on the other, then you know those two planes are parallel but not coincident, i.e. not the same plane. Okay, so what we can do here is simply divide. So one way of going about answering that question then would be to determine a point on the first plane. To determine a point on that plane, we could go about it by simply letting x equal 0 and letting y equal 0, and then solving for z. And if we did that, we would get that z is equal to 5/3. And then we could then show that 0, 0, 5/3 does not satisfy the condition for, that 0, 0, 5/3 satisfies the condition for the first plane, but does not satisfy the condition for the second plane, therefore is not a point on both. That's one way of answering this question, showing that the planes are not coincident. But another way of doing it is simply to divide the left side of plane 1 by 3, and if you do that, you get 3x divided by 3 minus 9y divided by 3 plus 3z divided by 3 minus 5 divided by 3 equaling 0. And for the second one, divide everything by 2. If you do that for the second plane, you'd get 2x divided by 2 minus 6y divided by 2 plus 2z divided by 2 minus 4 divided by 2 equals 0. And you would see that these planes are awfully close, but the d values are different, so they're actually not the same plane. In this next question, we're going to determine the acute and obtuse angle of intersection of those two planes shown. And we'll fall back on our knowledge that if you have the normal vector of one plane and the normal vector of another plane, the angle between those normal vectors will equal the angle between the planes themselves. And so this actually becomes a pretty easy question. The normal vector of the first plane is simply 4, -8, -3. And the normal vector of the second plane is simply 5, 15, or sorry, 1, -5, 15. So all we have to do is use the dot product to get the angle between those vectors, and that'll give us the angle between the planes themselves. So we know n1 dot n2 will equal magnitude of n1 times magnitude of n2 times cos theta. And ultimately, we'll get that theta, after doing cos inverse, is roughly equal to 93.5. Well, that's an obtuse angle. The acute angle will be 180 minus 93.5, which is 86.5. And so we'll be able to say that the acute angle between the planes is approximately 86.5, and the obtuse angle between the planes is approximately 93.5 degrees. Now in this next question, we're going to state the equation of the plane shown in vector equation form and in parametric equation form. So first thing we want to do to get it in those forms is to get 3 non-collinear points on the plane. So we want 3 points that don't all lie in the same line. To get a point on a plane in Cartesian form, like we showed earlier a few minutes ago, we're going to have to assign values to 2 of the variables x, y, and z, and then solve for the third variable. Because really what we have here is one equation with 3 unknown values. So in that equation right here, the one that I'm circling, that has 3 variables, why don't we let x equals 0 and y equals 0? If we do that, we see z equals 12. That means the point 0, 0, 12 is on the plane because it satisfies the condition of the plane. Now, let's just make up other numbers. Let's let x equal 1 and y equal 2. Well, if we let x equal 1 and y equal 2, we plug those values into this equation here, and we see ultimately that 0 equals z. So we now have a second point on the plane. And then if we let x equal 0 and z also equal 0, we'll be able to solve for y. And when we do that, we'll see that y is equal to -4, telling us that this point is on the plane. So we now have 3 points that are on the plane. So all we have to do is come up with the come up with a couple of direction vectors off of that. And we already know we'll be able to use any one of these points to be our position vector. So we'll use the vector 0, 0, 12 as our position vector, and we'll determine AB. Well, the vector AB is going to equal 1, 2, -12. If A is 0, 0, 12 and B is 1, 2, 0, the vector AB will be 1, 2, -12. And if A is 0, 0, 12 and C is 0, -4, 0, the vector AC will be 0, -4, -12. And so we'll be able to say we've got those 2 vectors there, and they can be, if necessary, used as direction vectors. So we'll use this as our first direction vector right here, 1, 2, -12. For our second direction vector, though, like I said earlier, we like it if our first non-zero component of a direction vector is positive. So it's technically not wrong to leave it like that, but we like it if that first direction vector if that first non-zero component is positive. So what we can do is multiply this whole vector by -1, and that would give us the vector 0, 4, 12. And that'll be, we could use that as our second direction vector. But the other thing that it's also a convention to do is to reduce it. If we multiply this entire direction vector by 1/4, we get a direction vector with all integers, but it's as reduced as can be, and the first non-zero component, which in this case is the y, is positive. Let's use that as our direction vector instead, the 0, 1, 3. So one of our direction vectors will be 1, 2, -12. Another direction vector will be 0, 1, 3. And we have a position vector that could be any of, the same numbers as any of the 3 points. We can use those as our position vector. And so, like it says here, that going back to the direction vectors thing we said earlier. And so we can say that the vector equation of the plane is as shown. The position vector 0, 0, 12, because we determined 0, 0, 12 is a point on the plane, plus a parameter times 1, 2, negative 12, plus a different parameter times 0, 1, 3. There's countless other vector equations of the plane. Based off of this, our parametric equations would be x is equal to 0 plus s plus 0t, which is s. Y would be equal to 0 plus 2s plus 1t. And z would be equal to 12 minus 12s plus 3t.